All right, guys, our goal today is to transform functions that are not parent functions. We're going to be taking our ideas of transformations and applying them to things that aren't parent functions. I hope we've already been seeing how powerful our ideas of transformations are and what they've let us do. Let's make sure we're all on the same page in terms of being able to use transformations to graph parent functions. So go ahead and find the graph of f of x equals 3 square root of x minus 2 plus 5. And hopefully we feel good about the square root parent function from our first unit. We know that this is going to be shifted 2 to the right. Remember, horizontal transformations are backwards from what we would think. And it's shifted 5 up. So here's where the vertex will be. And then, oh man, I wish I had chosen minus 5. And then from here, we're going to do, normally for the parent function, we would do square root of 1. So when we go over by 1, square root of 1 would be 1. But this multiplying by 3 stretches it. So instead of going over by 1 and up by 1, it will be over by 1 and up by 3. So it'll look up like this. When we do square root of 4, 1, 2, 3, 4, normally the square root of 4 would be 2, but that 2 is going to get multiplied by 3, and so it'll be up at 6. And so this has the effect of vertically stretching it by a factor of 3. How about the second one? What is the graph of y equals negative absolute value of x plus 2? And hopefully we feel comfortable that this is a shift left by 2. Remember that if it's inside the function, it's a shift left by 2. This is a shift up by 1. And then this is a reflection across the x-axis, a vertical reflection. So let's see what that graph looks like. Hopefully we feel good that absolute value parent function looks like this. And so when we take that important vertex point and shift it 2 to the left and 1 up, this is where the vertex will be. But this negative reflects it vertically. And so this absolute value graph will open up going down instead of up. So it looks like this. So that's the transformations on the absolute value parent function. And we can use transformations to find the equations of graphs. What is the equation of this graph? And hopefully we recognized that this was a quadratic parent function, or quadratic function. The quadratic parent function looks like this, and this one's also a parabola. So the question is, what transformations happened here? Well, I can see that the vertex shifted 1, 2, 3 to the left and 1 up. So I know the equation is going to have to shift it 3 to the right, we need x minus 3 inside the quadratic function. So x minus 3 is getting squared. Remember, it's backwards, so to go to the right, we need x minus 3. And we need it to shift up by 1, so we add 1 outside of the parent function, outside of the quadratic function. But we also need it to be concave down instead of concave up, so we need a vertical reflection, and so we need a negative in the front. One thing to pay attention to, and it didn't happen here, but when we go over by 1, normally the parent function, when you do 1 squared, is 1. So here, when we went over by 1, did it change by just 1? And the answer is yes. When we went over by 1, it went down by just 1. And so we don't need another number here. We just needed the negative. But we do, if this had gone down by like 3, we wouldn't just need a negative. We'd also need to put like negative 3 in front or something like that. That's if it had gone over by 1 and down by 3. So we want to look at that first point to be able to tell. How about this next one? We've got this square root function. What is the equation? And hopefully we notice that the square root parent function, normally goes like this. And so we can see it got reflected across the y-axis. We also see that that vertex point moved 1, 2, 3 to the right. So I'm going to start by saying I know it's going to be y equals square root of, I know it's x minus 3 because it's 3, the vertex shifted or translated 3 to the right. And I also need to say that to make it reflect horizontally, I need a negative inside the square root. And it's not just a negative like this. That's wrong. It needs to be a negative with this thing in parentheses. So negative x minus 3, or I could distribute that negative and make it negative x plus 3. Negative x plus 3. Okay, the last question is, okay, it's not reflected down, so we don't need a negative in front, but do we need a number? And the answer is yes. Normally when we go over by 1, it would be up by 1, which would be here, but this is only up by a half. And I can really see that when I go over by 4, 1, 2, 3, 4. Usually the square root of 4 is 2, but it only went up by 1. So I need a 1/2 here because that way when I do half of 2, normally it would look like this. Half of 2 would be 1, and you know, I could guess 1/2 from this point, but it's kind of hard to see. Really looking over to see like where it actually hit a whole number point, that's where I can really tell it. Okay, so let's hopefully we're all on the same page there. And now today, our goal is going to be to start talking about, well, what if we have a function that is not a parent function? Go ahead and graph this. Go ahead and graph this absolute value parent function. What does it look like? Well, hopefully from our warm-up, we're all on the same page, that this is shifted to the right by 1 and up by 3. So right by 1 and up by 3, that's where the vertex, normally y equals absolute value of x would look like this with a vertex at 0, 0. So I shifted 1 to the right and 3 up. And then absolute value parent function goes over by 1, up by 1, over by 1, up by 1. There was no, and it also makes a V-shape. So it's a constant rate of change of 1 unless it gets stretched. So here's our graph of our parent function. This is f of x. Notice that we use the same name for the equation in the table because these are the same function, just shown different ways. So we use the same name, f of x. What about a table? What are the different values of f of x for these different x values? Well, we can just plug in. So for instance, for -1, f of -1, we put in -1 for x is absolute value of -1 minus 1 plus 3. We need to do what's inside the grouping symbol first, so inside of the function. -1 minus 1 is -2. Absolute value of -2 is +2, and +2 plus 3 is 5. So we're putting in -1 and then evaluating using your middle school skills of evaluating. So this is f of -1. We can do the same thing for f of 0. So f of 0 equals absolute value of, we could put in 0 for x. 0 minus 1 plus 3. 0 minus 1 is -1. And the absolute value of anything is how far away it is from 0. Absolute value of -1 is 1. Always makes the number inside positive. And 1 plus 3 is 4. Another way we could have done this is we could have just looked at the graph. Look, when x is 0, y is 4. When x is 1, y is 3. When x is 2, y is back up to 4. When x is 3, y is up to 5. So we could use either the equation and plug in all those points, but the graph is oftentimes a lot easier to use than the equation when you're putting in a bunch of points. It's one of the useful things of a graph. So hopefully we got this table. Okay, now we're going to take this parent, we're going to consider this our original function, and we're going to do transformations on it. So let's look at how this works. Let's say we have g of x equals f of x minus 2. What does this minus 2, so here's our original f of x, it's this function, it's this graph, it's this table, all of these things are f of x written differently. What does doing f of x minus 2 do? And hopefully we recognize that because this is outside of the parentheses, this is a translation or a shift, doesn't matter which one we say, down by 2 units. So it's a translation down by 2. Now, let's actually look at how this is going to change the equation. So g of x is f of x minus 2, okay? So I'm going to rewrite it with f of x, what this equation is, plugged in. G of x equals, f of x is this. So I'm just going to replace f of x with what f of x is. F of x is absolute value of x minus 1 plus 3. This is f of x minus 2. I'm just going to put minus 2. Here's f of x minus 2. And we should notice that we can combine like terms. We've got plus 3 minus 2. And so this is g of x equals absolute value of x minus 1 plus 1. So this is the equation of g of x. Now, I want to show you a general rule. If we have a general function, g of x equals a times f of x minus h plus k, so this is our transformation form. This is what it's being stretched by, shifted left or right, shifted up or down. What happens when we add something to it? Well, h of x will equal this g of x, so a f of x minus h plus k, that's what g of x was, so this is g of x, plus w. And what will always happen is we'll just add it with the other one that's outside of the parentheses. We'll always be able to combine these. And so when you have an equation and you add something to it, you just add it to whatever the one is on the outside. It's not going to be a problem. And you'll notice that's what happened here. We had what was on the outside, this 3, and we subtracted 2, and now it's plus 1. So we had 3 minus 2 is positive 1. And that's the new horizontal thing. And this should make sense, right? Because initially it was shifted up by 3, and now we shifted it down by 2. And so now the vertical starting point is going to be 1. Okay, let's look at how the graph does. Well, again, this transformation is a translation down by 2. So that means every one of these points is going to come down by 2. So the easiest way to do it is to recognize that the type of function isn't changing. We can take this graph and just take the important point, the vertex, and shift it down by 2. So the new vertex, instead of being at 1, 3, will now be at 1, 1. And because the only thing we did was shift it down by 2, it's still an absolute value function. We can still go up by 1 and over by 1. And when we go to the left, up by 1, over by 1. And so we get this nice absolute value function. And the only difference is it got shifted, translated down by 2 units. And that's what this transformation does. So if we have a graph and it gets translated left or right or up or down, you leave what kind of function it is alone and just take the important point and move it. Okay. How about the table? We had this table over here and we shifted it down by 2. I think the easiest thing to do is just to take this new graph that we made. Take this new graph, what are going to be the new y values? Go ahead and look at this graph, and what are the y values at -1, 0, 1, 2, 3? What are those? And hopefully we saw that at -1, the y value is 3. At 0, the y value is 2. At 1, the y value is 1. At 2, the y value is 2. And at 3, the y value is 3. And what we might notice about the table is that this f of x minus 2, it's a translation down by 2. So all of the y values just got lowered by 2. 5 minus 2 was 3. 4 minus 2 was 2. 3 minus 2 was 1. And the x values don't change. Where those x values occur is exactly the same as they were before. We can really see that on the graph. The x values aren't changing. It's just where are the y's? All the y's are going down by 2. And so you can directly take a table and move it down by 2. Why don't you guys try this on your own? If h of x is equal to this original f of x, so here's this original f of x, plus 1, what is the new equation going? Well, first of all, in words, what in words is happening here? What is this translation doing? And hopefully we know that this is a translation or a shift f of x up by 1. So it's a shift of f of x up by 1. So what is the new equation of h of x going to be? So if the original f of x was this, and h of x is f of x plus 1, what is the new equation? And hopefully we can see that if f of x was absolute value of x minus 1 plus 3, if we add 1 to the outside, it's just going to shift it up by 1, and it's going to change this part. So it's absolute value of x minus 1 plus 4. We're just adding 1 on to the end here. Okay, so hopefully we got that. How about the graph of f of x? So we have this graph of f of x, and now we shift it up by 1. What's the new graph going to be? Well, instead of having a vertex at 1, 3, the new vertex is going to be at 1, 4. And it's still an absolute value function. So I'm going to still make my absolute value graph by going up by 1 and over by 1 in both directions. There's my new graph. Pretty easy transformation. How about the table? If this was the original table, and I now have h of x equals f of x plus 1, well, what's that going to do? The x values are not going to change. And all the y values, I hope you were able to find, just added by 1. So 6, 5, 4, 5, 6. Each of these y values was just added on by 1 because that's what shifting something up by 1 does. It changes the y values up by 1. Okay. Let's try a new type of transformation on a new function. So guys, this can be anything. It doesn't even have to be a type of function you know. These transformations will do the same thing, and that should make sense. You can take any function and shift it up by 3. Doesn't matter if it's a function we know, and when you shift it up by 3, all the y values will go up by 3. So go ahead and graph f of x equals square root of x plus 2 minus 1. Hopefully we should know that this is shifted to the left by 2 and down by 1, and the parent function of square root has a vertex at 0, 0, and square root of 1 is 1. The next square root we can do is square root of 4, which is 2, and it makes this concave down but increasing shape. So the vertex was at 0, 0. It's going to shift left by 2 and down by 1. Left by 2 and down by 1, and square root of 1 is 1. Square root of 1, 2, 3, 4 is 2. And so here is our, I guess I could go to 9. Square root of 9, that's kind of far over here, is 3. Ends up looking like this. And how about the table? What are the y values when x is negative 2, negative 1, 2, and 7? And of course we could do f of negative 2 by plugging in. So square root of negative 2 plus 2 minus 1. Negative 2 plus 2 is 0, so we're going to do square root of 0 minus 1. Square root of 0 is 0, so it's 0 minus 1, which is negative 1. Or, another way we could do it is just look at the graph. When x is negative 2, the y value is negative 1. When x is negative 1, the y value is 0. When x is 2, the y value is 1. When x is 7, the y value is 2. And so, the graph does show you a bunch of points at once, and it can make it a lot easier to do the table than just plugging in a bunch of numbers over and over again. So this is our original function, and we're going to be transforming it in just a second. Let's transform it. Here we're going to do g of x, the new function, is going to be f of x minus 3. In words, how is f changing? Well, hopefully we see that f is being translated or shifted right by 3. This is a horizontal transformation. This is different than the last one. Last time we had the minus 2 outside of the parentheses, and that was a translation down by 2. Now the minus 3 is inside the parentheses. It's inside of the function. You're doing f of x minus 3. And this is a horizontal translation, and it's backwards from what you might think. The horizontal things that are inside the function this is to the right, not to the left. And so how is the equation going to look? Well, let's actually do f of x minus 3. F of x minus 3 means you put in x minus 3 where x is. So where the x is, we're going to put in x minus 3. So g of x is, so here's f of x, square root of, instead of x, we put in x minus 3. That's what f of something means. F of whatever it is tells you to put that in for x. So x minus 3, that's what our x was, plus 2 minus 1. And we can see that when we put x minus 3 in for x, the minus 3 and the plus 2 will combine because they're both inside of the square root. This minus 1 can't combine because it's outside of the square root, but both of these ended up inside. And so g of x equals square root of x minus 1 minus 1. Now, how is this going to work generally? Well, let's go back to our general formula. If we have any function, a times f of x minus h plus k, and we do g of x plus w, that means we're going to take this x plus w and put it in for x. So let's look at this. I of x will equal a times f of, instead of x, we're putting in x plus w. So we're putting in x plus w here. So x plus w minus h plus k. And so you can see that this will always combine with the other one that's inside of the function. And an easy way of thinking that is just like, hey, whatever you're doing here, just do it to the inside part. Look what happened here. There was a plus 2. We did minus 3 inside of the function. So it's 2 minus 3 was negative 1. So we just took what was already in there and did minus 3 to it because we were doing x minus 3 inside of the function. So 2 minus 3 gave us the -1. And this -1 just stayed the same, right? We didn't do anything to the outside vertical shift. We just shifted it to the right. And this should make sense, right? We are shifting it to the right by 3. That's not going to change the vertical shift. It'll change the horizontal shift in the inside. Let's look at how this looks on the graph. This is a, I'm going to rewrite this, f of x minus 3. This was a shift to the right by 3. And so this original graph is going to the right by 3. So instead of having a vertex at -2, -1, that's going to go to the right by 3. And it will be at +1, -1. Now, we shifted it to the right by 3. It's still going to be a square root function, and so we can still make a square root function like we normally... Oh, you guys couldn't see that. I'm sorry, guys. That was a little bit off the graph. I apologize. This shifted to the right by 3, and so now the vertex will be at +1, -1. But it's still going to be a square root graph, and so from here, if this is the vertex, we can just do square root of 1 is 1. Square root of 1, 2, 3, 4 is 2. So I can still make my square root graph like normal. Another thing I could have done is just shifted every point to the right by 3, 1, 2, 3, and we'll see that it's going to be at 2, 0. This is over 1, 2, 3, and so we can see it'll be at 5, 1, which it is. Okay, so we're shifting to the right by 3. We weren't doing a parent function to the right by 3, we were doing this original function to the right by 3. And still pay attention to that vertex point. How about the table? How are we going to do the table when we shift to the right by 3? Well, I want you to notice what happened on the graph. Well, let's look at, we can just create the table from this graph. This point is when x is 1, y is -1. What are the other points? Well, when x is 2, y is -2. Oh, sorry, when x is 2, y is 0. And when x is 1, 2, 3, 4, 5, y is 1. So when x is 5, y is 1. And what you might notice is that compared to the original table, the y values are the same. -1, 0, 1. They didn't change. What changed this time were the x values. And that should make sense because we didn't change what the y values were. We just shifted to the right by 3. So every y value is going to be in the same place. It's just that the x values moved to the right by 3. And moving to the right by 3 is adding 3 to the x values. You might think this would be subtracting 3, but it moves it to the right by 3. Notice that all of these x values added 3. -2 plus 3, +1. -1 plus 3, +2. 2 plus 3, 5. So what's this last point going to be? Well, when the old x was at 7 and the old y was at 2, when we shift it to the right, now instead of being at 7, it's going to be 3 to the right. The x value needs to be added by 3. This will be at 10, and the y value will not change. It'll still be at 2. So by shifting something to the right, we don't change the y value, we only change the x value. Now, what's the shortcut way to think about this? Well, if you're shifting to the right, you're just adding 3 to all of these x values. That's what shifting to the right by 3 does. Add 3 to the x values in the table. Okay, try this on your own. What if we take this same parent function and we do f of x plus 1? What transformation will this do? We should realize that this is inside the function, so it will translate left by 1. If this plus 1 had been on the outside, it would have translated up by 1. Remember, it's backwards from what you might think when it's on the inside. It's left by 1. Okay, so what is the equation going to be? If this was the original equation, and we do f of x plus 1, well, this plus 1 on the inside, I hope you see, it's just going to add 1 to the inside in here. So it's going to be square root of x plus 3 minus 1. So the y transformation didn't change. Still going to be a -1 here. It's still a -1. But the inside part, since we had f of x plus 1, we added 1 to the 2. So originally we had f of x equals square root of x plus 2 minus 1, and we just added 1 here because it was f of x plus 1, and so the inside got added by 1. Okay, how about the graph? Well, we knew the original graph was this guy. And so when we translate it left by 1, the new vertex, instead of being at -2, -1, will be at -3, -1. It'll be shifted 1, 2, 3. It's shifted 1 to, it used to be right here. Oh, you guys can't see that. I'm so sorry. The vertex used to be here at -2, -1, and we shift it 1 to the left. And then we just make a square root function from here because we didn't change what type of function it was. We just changed the translation. So square root of 1 is 1, 1, 2, 3, 4. The square root of 4 is 2, and the square root of 9 would be 3. That's going to go over here. How about the table? If we have this original table, how is f of x plus 1 going to manifest itself here? Well, it's shifting left by 1, and so the y values are not changing. The y values are still going to be -1, 0, 1, and 2, just like they were up here, -1, 0, 1, and 2. But where they happen is going to be to the left by 1, and so the x values from what they used to be needed to go down by 1. So -3, -2, 1, and 6. So I just took each of these x values and I subtracted 1 because if the x values move to the left, all the x values need to be less by 1. Hopefully we're feeling okay about that. How about this last one? What are the transformations that are happening to f of x here? Hopefully we notice that this is 4 units to the right and 1 unit up. So what's the equation going to be? Well, this is going to affect the left and right part. So the original equation was f of x equals square root of x plus 2 minus 1. This is going to change this part, and this is going to change this part, right? So the new one, m of x, will be -4 on the inside, so square root of x minus 2, and plus 1 on the outside. -1 plus 1 is 0. We don't need to put plus 0. We just won't put anything there. Now, how about this graph? You know, we've been talking about shifting the original graph, but you can always just use the shifted equation. If you change the equation, well, this is what the new graph is going to be. It's shifted, if this is the parent function, y equals square root of x, shifted to the right by 2. So it's to the right by 2 from the parent function. Square root of 1 is 1. Square root of 4 is 2. We get a graph that looks like this. Now you'll notice this point will be shifted 4 to the right and 1 up from where the old vertex was. The old vertex was at -2, -1. If we shift it 1, 2, 3, 4 to the right and 1 up, there it is at 2, 0. So 2 ways to do it. You can change the equation and then graph it, or you can just change the graph directly. Okay, let's look at what is a slightly harder transformation in my mind. So here is an original function, f of x. Go ahead and say, what is the equation for f of x? What is the equation here? And we should say this is the quadratic parent function, which normally has a vertex at 0, 0, shifted right by 2 and up by 1. And when we go over by 1, it's still going up by 1. 1 squared is 1, so it wasn't stretched at all. So this is just, I'm going to call it f of x because that's what the name was over here. F of x equals, to shift it to the right by 2, I need x minus 2 squared. And to shift it up by 1, I need a plus 1 on the outside. So that's our original function. What about the table? I could put in these points for x and evaluate them. The easier way is just to get it off of the graph. Looks like 1, 2, 3, 4, 5. When x is 0, y is 5. When x is 1, y is 2. When x is 2, y is 1. When x is 3, y is 2. And when x is 1, 2, 3, 4, y is 5. So I can just take it directly off of the graph and get that table. So this is my original function, and we're going to transform it. Here, we're doing g of x equals 3 f of x. And 3 is, when there's no operation in between, this means it is multiplying 3 times f of x. So what is the transformation this is doing to our original function? Well, hopefully we recognize that we're multiplying by a number that is bigger than 1. So this is vertically stretching by a factor of 3. The big difference here is that always before we were vertically stretching functions that were starting at y equals 0. And when you do 3 times 0, it's still 0. It never moved the vertex. But now we don't have a vertex that is 0, and you'll see that it will in fact move the vertex. Let's look at it. The equation of g of x. G of x says it is 3 times f of x. So I'm going to do 3 times, I'm going to take f of x from up here. F of x is equal to this. So this is going to be 3 times f of x, and what f of x is x minus 2 squared plus 1. Now I need to be careful. I'm going to write it wrong for just a second. This is wrong. Why? Why is this wrong? It's wrong because it's supposed to be 3 times all of f of x, but the way this is written, the 3 is only multiplying times this part. To make it actually multiply times everything, I need parentheses around this, because f of x is a binomial. It's x minus 2 squared, that's the first term, plus 1. And that 3 is going to distribute to both of them. And that's what we're going to do right now. G of x equals, this 3, whenever there's a plus or a minus, it will distribute. The 3 will multiply times the x minus 2 squared. And it can't multiply inside of here because this is being squared, so we just leave it in front. 3 times x minus 2 squared. So that's 3 times x minus 2 squared. We can't simplify it because this 3 cannot multiply inside of here because of the squared. So 3 times x minus 2 squared plus the 3 also needs to multiply times the 1. 3 times 1 is 3. And so what we'll see is that we end up with the vertex used to be at 2, 1. Now the vertex will be at 2, 3. It's to the right by 2 and up by 3 from the parent function y equals x squared. So I'm going to use this new graph to graph it. It's 2 to the right and 3 up. So I'll go ahead and graph this on your own. You can graph this on your own. Graph g of x equals x minus 2 squared plus 3. So this is 2 to the right and 3 up. And it's getting multiplied by 3. So normally we would do 1 squared is 1, but it's getting multiplied by 3. So 1 squared is 1, 1 times 3 is 3, so it needs to go up by 3. And it'll be the same on the left side. And we can tell, like, look compared to the parent function. This is going up way faster. This first point normally went up by 1. Now it's going up by 3. It would have been here and here. It got vertically stretched, but it also changed the y-intercept. So be careful, because this will multiply both by what it's stretching by and what it is, like what the y-intercept was. So for instance, let me just give you a quick example. If we had the original function, f of x was 2 absolute value of x plus 1 minus 7, and g of x equals 5 f of x. Well, notice that it didn't mess around with what was inside the function because you can't multiply inside of the function. But when you do it, it'll be 5 times 2 absolute value of x plus 1 minus 7. The 5 will multiply times this term and times this term. 5 times 2 is 10 absolute value of x plus 1. We don't change the function. But 5 times minus 7 is minus 35. It will change both this number and this number. This is all one term, and this is one term. So it's like 5 times 2x minus 7. The 5 will multiply times the 2. Doesn't change what the x is, minus 35. So it'll never multiply inside of the function, but it will change the coefficient. Okay, how do the y values change? Well, I can pick them straight off of the graph, or at least I can see some of them. When x is 1, y is 6. When x is 2, y is 3. And when x is 3, y is also 6. So I could see those from the graph. What's happening here to these y values? Notice that these x values are the same, so the x values didn't change. Vertically stretching something didn't change where the x values were. It did change the y values. How? Well, it changed it just like you might think it would. It multiplied all of the y values by 3. That's what 3 times f of x does. It's 3 times all of the y values. 2 times 3 is 6. 1 times 3 is 3. 2 times 3 is 6. So what are these y values going to be here and here? They're going to be 15 and 15, because 5 times 3 is 15. 5 times 3 is 15, and that's what 3 times f of x is going to do. It's going to multiply those y values by 5. This is another form of multiplying. When you have a negative in the front, it is a type of multiplying, but what transformation does it do? And hopefully we recognize this is a reflection across the x-axis. It's a vertical reflection. And this is the same as multiplying by -1. So let's see how this affects the equation. Our original equation was f of x equals x minus 2 squared plus 1. If we do negative f of x, that's going to be negative of this. And this is a binomial. That negative needs to have, it's going to do negative of the whole thing. So x minus 2 squared plus 1. The negative will be the negative of this. It can't go inside of here because this is being squared, but it'll be h of x equals negative x minus 2 squared, but the negative will also be a negative of positive 1, which is negative 1. That negative distributes because it is a form of multiplication. It's the same as multiplying by -1. -1 times this and -1 times this. So there's our new equation. Notice that the negative changed both the multiplication value and the minus and the y-intercept. So let's look at how it looks. When we graph this, go ahead and graph h of x on your own based on this equation. So it's 2 to the right and 1 down. There's where the y value is. There's where the vertex is. And this negative makes it open downwards. 1 squared is 1, but it's going to be negative. -1 squared is 1, but it's going to be negative. So it's going to end up looking like this. Right? So we get this like parabola going down. Now what I want to show you is compare that to the original graph. I don't know if you guys can see this. Notice that the whole thing reflected across the y-axis. The original one was like this. This is a reflection across the x-axis, but the y-intercept will change. The parent function usually starts at 0, and so when we reflect it, it doesn't change the vertex. But when we reflect this one, the vertex doesn't just come right here. It ends up being down below here. So a +1 vertex will have a -1 when you do it. How about the y values? What are the y values at 0, 1, 2, 3, 4? We can get them off of the graph, or we can recognize it's just the negative of all the original y values. So here was the table. We're just going to do negative of the original y values. So it's -5, -2, -1, -2, -5. I just made all of the y values negative because that's what this equation says to do. H of x is just negative of all the y values. Notice that the x values did not change. All right, how about if we do two things at once? M of x is -2 f of x plus 3. What are the transformations here? Well, we are reflecting across the x-axis. That's what the negative does. Vertical stretch, because 2 is bigger than 1. And we have a shift up by 3 because of the plus 3. So there were 3 things happening here. How about the equation? Well, this says we do -2 times f of x. And again, f of x was, what was the original one? X minus 2 squared plus 1. If we do -2 times it plus 3, let's just do what the equation says. It says do -2 times f of x. F of x is a binomial, so I need to put it in parentheses. So -2 times f of x, and then it said plus 3. So we're going to put plus 3 on the outside. And when I do this, the -2 will distribute. It can't multiply inside of this squared, but it's going to be -2 x minus 2 squared. -2 times 1 is -2. And so this will be m of x equals -2 x minus 2 squared, and the -2 and the 3 can combine because they're both not in any sort of a function. So it's +1. So kind of crazy stuff here, guys. How about the graph? What's the graph of this equation going to be? Well, it's shifted 2 to the right from the parent function. So we can still use our parent functions to graph things. It's very helpful. +1. And then it's reflected and stretched. So when we go over by 1, 1 squared is normally 1, but it's getting multiplied by -2. So it'll be down by 2. Over by 1, down by 2, and it'll make a parabola. The next point would be 2 squared is 4. 4 times -2 is -8. It would be like down by 8 from here. Okay, how about the y values? Well, did the y values get shifted left or right at all? No, there was no horizontal change. And so the y values are still the same as they were, or sorry, the x values are still the same as they were before. But what about the y values? The order of operations here says you multiply by -2 first and then add 3. So that's what we're going to do. We're going to take these original y values and we're going to multiply them by -2 and then add 3. 5 times -2 is -10. -10 plus 3 is -7. The next y value is 2. 2 times -2 is -4. -4 plus 3 is -1. 1 times -2 is -1 plus 3 is 2. We've got, something seems wrong here. Hold on. 2 times -2 is 4 plus 1. 1 times, is 1. Sorry. 1 times -2 was, 1 times -2 is -2. -2 plus 3 is +1. And then they'll repeat on the other side because it's quadratic. So -1, -7. And I guess we could have gotten that off of the graph, right? So we've got -1, -1, sorry, 1, -1, 3, 1, sorry, 2, 1, my goodness, 3, -1, and then the next one would be 4, -7. So tricky stuff. All right, guys, that is all the new stuff for today. I'd like to give you a minute to practice before you get to your homework where you're actually getting some feedback right away. So here is some practice. Let's practice with equations first. If here's our f of x, and we do g of x equals f of x plus 5 minus 1, what will the new g of x be? And hopefully you got it that this will add 5 on the inside, and this will subtract 1 on the outside. And so g of x will just be 2 times x plus 2 plus 3. So we did adding 5 on the inside, -3 plus 5 is +2. And on the outside, the vertical ones will also combine. 4 minus 1 is 3. Over here, if f of x is 3 absolute value of x minus 1 plus 4, then 2 f of x will be. Well, hopefully we remembered that when we do 2 times this function, it ends up distributing. So it'll multiply times here and times here. And so 2 times 3 absolute value of x minus 1 is 6 absolute value of x minus 1. And then that 4 also gets multiplied, so plus 8. So the 2 will multiply times here and times here. How about this exponential one? 2 to the x plus 5 plus 3. What if we do f of x plus 3 plus 2? Well, g of x then will equal, if we add 3 on the inside, that adds inside the function. It'll be 2 to the x plus 8, and the plus 2 will add to the outside, plus 5. Last one, if we do -3 here's f of x. If we do -3 f of x plus 7, -3 of f of x is going to be -3 times all of this will be -6 square root of x minus 3 minus 21. The -3 will multiply times this and times this because it will distribute. F of x is a binomial. So -3 when it multiplies here and here. But then we also need to add 7. And that plus 7 will add just to the outside part. So the order of operations matters here. We multiply and then we add 7. So we multiplied and then we're going to add 7 and we'll get -6 square root of x minus 3 minus 14. So notice the inside part never changed because there was no shift left or right. How about the graphs? If this is f of x, oh, you guys couldn't see that. If this is f of x and g of x is f of x plus 1 minus 2, graph it. You can do it straight off of the graph. You could have found the equation, changed the equation, graphed the new equation, but recognize this is just a shift by left by 1 and down by 2. So we can take this vertex and go left by 1 and down by 2, and the new vertex will be at 1, 1. I see it went down by 1 on both sides, and so we'll go down by 1 on both sides again. 2 squared is 4, so it'll be down by 4. There's my parabola. I just shifted it left by 1, down by 2, and I can do it straight off of the graph. How about h of x is negative of f of x? Well, this is going to reflect across the x-axis. Take the vertex. It's going to reflect, instead of being at 2, 3, it will be at 2, negative 3. This is where the new vertex will be. It got reflected across the x-axis. It's going to come down to here. So 2, negative 3. And then instead of being concave down, it's going to be concave up. So the new one will look like this. Hopefully we can see that that's what happens when you reflect across the x-axis. Here we have f of x is this square root function. Ooh, this is different. What about f of 2x? Okay, so we haven't done any example just like this today, but we should know from our last lesson, f of 2x. This is remember if it's this is horizontal because it's inside the function. And it's backwards from what you might think. This is not a horizontal stretch. This is a horizontal compression by a factor of 1/2. Every x value is going to be half as far over as it normally would be. So this x value is at 2. It's going to be half as far over as it normally would be, and it will be at 1. This x value is at 3. It will be half as far over as it normally would be. Half of 3, so this is at 3, half of 3 will be 1.5. This x value is at 1, 2, 3, 4, 5, 6, and so it'll be half as far over. It'll be at 3. 1, 2, 3. And so we end up, this was horizontally compressed. It's like we took this and pushed it in towards the x-axis. Every x value was half as far over as it normally would be. So we just left the y values alone, and we pushed in the x values half as far as they normally would be. How about this one? What is f of negative x? Well, hopefully we recognize that this is a reflection across the y-axis. It's a horizontal reflection. So every x value will be reflected across to the other side of the y-axis, and the y values will stay the same. So this x value that was at 2 will become at negative 2. This x value that was at 3 will go to negative 3. It gets reflected across the y-axis. This x value at 6 will go to negative 6. So we end up with a graph that looks like this. I think this is supposed to be 1 over. Sorry. So you can see how the f of negative x reflects across the x-axis. Now you could have done it by putting in negative x in for the function and graphing it from there, but this is better. Let's take a table. If you have f of x minus 3 plus 5, this is a shift to the right by 3 and up by 5. If we shift to the right by 3, that's changing these x values. They will all be 3 to the right. That means we need to add 3 to all of these. The new x values will be 4, 5, 6, 7. I added 3 to all of these x values because they went to the right by 3. Going up by 5 adds 5 on to all of the y values. So all the y values will be 10, 7, 2, and 12. I just added 5 to all of these and added 3 to all of these. Shifting to the right adds 3 to the x values. Shifting up by 5 adds 5 to the y values. So those both changed here. h of 3 equals 3 f of x plus 1. Notice there's no shift left or right. And so the x values are going to be the same. 1, 2, 3, 4. But the y values got multiplied by 3 and then added by 1. And the order of operations matters here. We have to take the y values and multiply them by 3. So 3 times 5 is 15. And then 15 plus 1 is 16. Here, we're going to take this y value and multiply it by 3. And then add 1. 2 times 3 is 6. 2 times 3 is 6. 6 plus 1 is 7. So we're just doing what it says to do to the y values. 3 times negative 3 is negative 9. Negative 9 plus 1 is negative 8. 3 times 7 is 21. 3 times f of x, 3 times 7 is 21. 21 plus 1 is 22. So we're just doing, when we're doing a table, this is telling us what to do to the y values. Here it's telling us what to do to the x values before we get the right y value. I hope you guys have a good rest of your day. This is the last of our long lessons. We should go back to having much shorter lessons.